All right, section 7.1 is how to find the area of a region between two curves. So up to this point, all of the areas that we have found with calculus are between the curve and what? The x-axis, right? We always measure the area from the curve down or the curve up to the x-axis. So what we're going to be doing now is we're going to be taking two curves. So draw this in if your computer didn't print it off correctly. And what we want to do is we want to find sort of the shaded region that's in green. Okay? So imagine, if you would, that you actually just wanted to find the area of f of x all the way to the x-axis. That would be the integral, right, of f of x between a and b. And then if you wanted to find the area that was underneath g of x down to the x-axis, that would be the integral of g of x from a to b. So in order to find the area trapped between them, the way that we do that is we take the integral from a to b, and this is basically taking f of x dx minus the integral from a to b of g of x dx. Right? If we took all of the area down to here and then we subtracted off the area that's just whited out basically, we're going to have that trapped green area. Okay? And we can actually do that in a more concise form because our properties of integrals say that if I'm subtracting two integrals, it's the same thing as subtracting the functions themselves and then integrating them. So we could do that and receive the same answer. And sometimes it's more helpful to do that, especially if the two functions are similar and they could combine in some way, right? Okay, so let's take a look at this one. We're not actually finding the area, we're just shading it. So I want you to give you an idea of how we do that, and then we're going to use the next two examples after this to actually do the whole process. This says to sketch the graph corresponding to the following integral and shade the indicated area. So go ahead and take your calculator. I know you could do these without, but some of them are a little more complicated and you can't. So let's just use our calculator as our device to do this. And what I really want you to recognize is the first function in parentheses is operating like f of x. And the second piece is operating like g of x. So we're going to put into y1 2 minus x squared. And into y2 we're going to put x squared. My calculator. Let me try one more time. There it is. All right, so this is what you have. And it tells us that we want this to be from -1 to 1, right? So if you'd like, you can make your window simply from -1 to 1, or if you want to make it just a little bit bigger to give yourself some perspective, you could make it, say, from like -2 to 2, and understand you're not going to go to the full edges of it. You're welcome to do just a standard 10 by 10 window on the Ymin, Ymax. There's another feature that's called Zoom Fit, which is Zoom 0 in your calculator, which will, in theory, automatically pick you the best Y window possible for the function you gave. And on this one, it does pretty well. So I've got two parabolas. One is an upward parabola, and the other one faces downward. And they overlap. And can you tell where they're overlapping based on your graph? They're overlapping at 1 and -1. Okay, so my graph's not going to be perfect, but you guys can probably make do with the idea of what I'm sketching, right? So this is -1 and this is 1. And what it says to do is to sketch the graph corresponding and then to shade the indicated area. So the area that we'd be finding if we did this is we'd be finding this sort of footballish shape in the middle, right? So that's what we would actually be finding if we found the difference in these two areas individually. Okay, so this is sort of the first step in all these problems. This problem just has this only step. But on the next one, we're going to use this and we're going to go one step further. Now, there's another interesting feature going on the next one. So as I flip to this, tell me if you can see what interesting feature is going on in this problem. So sketch the region, find its bounded area. What weird thing is going on in this problem? Do you see it? These do overlap, actually. They will. We have a curve and a line. Okay, so that's an interesting feature. We didn't have that on the last one. Yeah, and that's actually really important. These are with respect to y. So as we look at this function, the input is actually y instead of x. So if you had like y equal x squared, it would open up, right? But this is essentially x equal y squared. What does the graph of x equal y squared look like? Yeah, it's a sideways parabola. So as we're sketching this one I can't draw on the calculator because my calculator only lets me do functions, at least in a convenient way. We'll explore some other things to let us do later. But it won't let us do this very easily. So as we're looking at sketching this, we're going to have to sketch this by hand. So we've got y squared, so it opens like this. And I've got the graph of y plus 2, x equal y plus 2. So this was x equal y squared. This is x equal y plus 2. So if I solve this for y, this is y equals x minus 2, right? So I could sometimes change these to actually get my graph to be able to think about it from a function perspective in respect to x. So I'm going to use gray on this one. This one is crossing the y-axis at -2. And then it will be a line with slope 1. So since it has a slope of 1, it's actually going to cross the x-axis over here at 2 as well. So the graph looks something like this. Okay, so there's the first issue. Now, in order to do this problem, what you will notice, as opposed to, say, this one over here, is that this one is already set up in integral form, right? Which meant you knew that even without graphing it, that we were going to start at -1 and we were going to stop at +1. Nothing tells us that on this graph, does it? So we actually have to figure out where these are actually crossing. Sometimes it's easy to see, especially if you've got your calculator and you can graph it on there. Sometimes you have to do a little algebra to get it, and on this one it's not too bad. What we want is we want these two to be equal to one another, right? So we want our y squared to equal y plus 2. How do we solve an equation like that? I know you guys know the answer, so somebody tell me. You could complete the square. I think it's probably easier than that. We can't plug in for y because we don't have... Thank you. All right, so we're going to subtract it to the same side. And we could do the quadratic equation, or in this case, what could we do? Factor. How will this factor? +1 and -2. So the two y values here that we get are y equals 1 and y equals -1, and then y equals 2. Of course, those are the y values, and because our integration that we're about to do is with respect to y, we're in good shape to use those, right? So our integral that we're setting up will be the integral from y equal -1 to y equal 2. Now, the next thing that we have to recognize is which graph is on top, because we're supposed to be subtracting from the top to the bottom one. So what's the top graph? It's y squared. So remember the shaded region, I didn't shade it in, maybe I should have, is right here. And on this part of the region, this graph, f of y, is on top. And this graph, g of y, is on bottom. So we're going to have our f of y graph, which is x squared, not x squared, y squared on top minus the g of y graph, which was y plus 2 on bottom. And then I have dy. Now, in some cases, you could actually change these into x and do everything with x's. That would be fine. It would not be very helpful on this one. And the reason that it wouldn't is because this graph, the first one that I drew in black at y squared, is not a function on the whole interval that I'm looking at, right? Remember, in order to be a function, it would pass that vertical line test, so it's not a function with respect to x. So I can't just turn these into x values and do it from a perspective of x. It won't work like that. So you have to be a little bit careful on that. All right, so doing this one, I have y squared minus y minus 2 dy. So what's the antiderivative of y squared minus y minus 2? All right, y cubed over 3. What's next? Y squared over 2. Promise I'm not trying to trick you guys. And the last one? Minus 2y. And we're evaluating these at 2 and negative 1. Okay, so we're going to have 2 cubed over 3, that's 8 thirds, minus 2 squared over 2, that's 4 over 2, which is 2, minus 2 times 2, which is 4. All of that minus. Negative 1 cubed would be negative 1 over 3. Negative 1 squared would be 1 over 2, and then a subtraction of the value that was already there. And then negative 2 times negative 1 would be plus a 1 right here. Is that good so far? Oh, I'm sorry, it was a 2. I was more concerned about the positive. Yes, it's a 2. Thank you. Positive 2. Alrighty then. If we combine all those values together, somebody tell me what your calculator will get if you simplify for me. Do you know what that is as a fraction, Abby? Did it tell you? Change it back into a fraction? Is that what you got too, Caleb? Maybe it would have been faster if we just... Negative 7/6? What did you get? Is that what you got, Evan? What did you get? Negative 4.5 is what I have written down. Is that what you have too, Kaylin? Okay, I think there's probably a sign error in what you've got going on, Abby, so we can check it out in a little bit. Negative 9 over 2, or negative 4.5. Now, I want to pause for a moment and ask you if that makes sense. Does it make sense that the answer should be, in particular, negative? No, because why? Yeah, it should be subtracting the bigger one from the smaller one, so we should be getting a positive, right? So does anybody have any idea when we worked this problem, I don't know how to say this, but kind of what we did wrong? Do you know, Hannah?
I mean, not really, but I felt like it should have been the other way around, so it's perspective of y-axis.
Yes, that's what I want you to say. Okay, so say that again from the perspective of the y-axis. What did you think?
If it's from the perspective of the y-axis, then the y plus 2 becomes y.
Yeah. So I'm going to draw a rectangle and I use this example on purpose because we're going to see something happen in the next section in 7.2 that's very similar to this. And it's easy to make the mistake, if you will, that we did. That's supposed to be a rectangle, okay? Pretend for a moment it is. Normally, when we're looking at our graphs, say for instance right here, what we're doing is we're finding rectangles like this, right? They're rectangles from the top function down to the bottom function because we're doing everything with respect to x. On this function, when we're working with respect to y, the rectangle should have been drawn horizontally. And so Hannah's exactly right. We should have subtracted it the other direction. And if we subtract it the other direction, what's it really going to change in the end? Just the negative. It's just going to change the sign, correct? So the easiest thing to do is honestly not to worry about which one's on top or on bottom. What do you think the easiest thing to do would be? We should always realize it's going to be positive. That sounds like an operation that we know in mathematics. Absolute values. So the easiest thing to do is to put absolute values around what we're doing, and then does the subtraction order matter? Nope, it doesn't matter at all. And then we don't have to worry about which one's on top or on bottom if we're doing this from the side or from, from the vertical direction or from a horizontal direction. This isn't the only way to do it. I just want to bring that up so that you can see that it's another way of thinking about the same problem, is to think about it in terms of absolute values. All right, the next one is a little more interesting even than this one. We had some more kind of absolute value in this g of y function business. This one's got some trig in it. That makes it interesting for one. But it also does something else that's very interesting. So I'd like for us to take a chance to graph this first. So go ahead and take your calculator. Make sure you are in radian mode. You should be. But put in f of x equals 2 sine x for y1, and then g of x equals tangent x for y2. And make sure, this time, let's just set our window exactly to go from negative pi thirds to pi thirds. And I'm thinking, I'm going to try zoom fit and see what happens. I'm not sure if it'll be helpful or not. Oh, it's pretty good. Oh, you can't see my screen. I'm sorry. But I like that. Does it look like a propeller? Looks like those propeller leaves to me, the ones that float down from the trees. Kind of looks like that. What unique things happening here that we didn't see happen in the last problem or the other two examples that I showed you pictures of? There's two pieces, right? The graph actually crosses itself sort of, in this case, in the middle, but somewhere in between it crosses. So there are two pieces of this that we have to find the area of. In particular, we have to find the area from this to here, from the left-hand side to the middle, and then from the middle to the right. And on this one, we know that this is symmetric, so we could just find one piece and double it. But in general, of course, there's nothing that would say that every function would have that ability, that it would be symmetric. So I'm going to treat it like it's not symmetric for the moment, just so you can see how you'd set it up if it weren't. Does that sound okay? Did you get something weird, Seth?
Yeah, I got some.
Okay, let me take a look. Anybody else get anything weird, graph-wise? Something weird here? Let's hear about it first. Yep, that's it. Okay, anybody else having visual issues with their calculator? Okay, so the cool thing I want to make mention of here, though, as well, is they've given you a very friendly graph in the sense that they actually told you it went from negative pi over 3 to pi over 3. So they told you the endpoint negative pi over 3. You can see on your graph that this stops at 0, and then it's going to go from 0 to pi over 3 after that, right? So in that sense, this is a very friendly problem. All right, so let's take a look at how we would write this problem out. I'll sketch a graph on my screen just so that we have it as a reference. Not perfect, but it doesn't have to be. So this is negative pi over 3 we're at 0 in the middle, and then we're at pi over 3 on the right. All right, so our graphs, antiderivative that we're looking at here is going to go from negative pi thirds to 0. And then we're going to add what happens when we go from 0 to pi thirds. And of course, we're all going to recognize that this is going to give us the same value twice because this graph is symmetric. And then this is the case where you could figure out which graph's on top and which one's on bottom if you'd like. That's fine. Or you can say it doesn't really matter because all I'm going to do is to take the positive part anyway. So I'm going to use some absolute values, and that's what I'm going to use. So this is 2 sine of x minus tangent of x. Now I'm running out of space. Let me move this guy over a little bit. Dx plus the integral from 0 to pi thirds of, again, the absolute value of 2 sine of x minus tangent of x dx. You can pretend like you can see it all on my screen. It's almost all there. Nice. All right, these are antiderivatives that for the most part you know. Or at least you should. I hope so. What's the antiderivative of sine? Negative cosine. So this is negative 2 cosine of x. What's the antiderivative of tangent? The derivative is secant squared.
It's like negative.
It's okay, I cheated too. I looked down. It's natural log
Yeah.
of cosine of x. We've got absolute values in there as well, and then we've got another absolute value on the outside. And this is from 0 down to negative pi thirds. Okay. And then we've got the other half of this, which looks like the same thing, but the limits of integration, of course, are different. So negative 2 cosine of x. And then it was minus, I'm sorry for tangent, this was minus already, so this should have stayed minus. The eraser is really thick. And it's from pi thirds here down to 0. All right, so if I plug in, what do I have here? 0. I've got 0 plugged into cosine. Let's see if we can do this as we go. What is cosine of 0? 1, and then it's times the negative 2, so it's negative 2. Cosine of 0 inside of a natural log. What's cosine of 0? 1. What's the natural log of 1? This is 0. What's the natural log of 1? This is 1. What's the natural log of 0? Of 1. I keep saying it. I'm sorry. The answer is 0. Okay, the natural log of 1 is 0. This is minus 0. So then minus, and now I'm going to plug in pi over 3. That one's harder. Okay, so what's the cosine of pi over 3? Cosine of pi over 3. It's 1/2. Yeah, it's 1/2, and then it's times the negative 2 that's out there. So this is negative 2, and then times 1/2. And then we have minus the natural log of another 1/2 over here. Plus. Oh, I was supposed to plug in negative pi over 3, so I think I meant negative 1/2 actually. Because I was at, no, I'm not. I'm at pi half. I'm still at 1/2, aren't I? For negative pi over 3 for cosine, because I'd be in quadrant 4. Cosine's positive in quadrant 4. So it's the same. Okay, plus. Now I'm going to plug in the value pi over 3. Let me underline it in red. At this point, I'm doing this piece, so I'll write this one in red. So plus, now I'm going to have negative 2, and I've got the cosine of pi over 3. So this is negative 2 times 1/2, again, because it's pi over 3. Minus the natural log of, again, 1/2. And this is supposed to be minus. And I'm supposed to plug in 0. So when I plug in 0, I get negative 2 times the cosine of 0, which is 1, so that's negative 2. Minus the natural log of cosine of 0, so that's the natural log of 1, and the natural log of 1 is 0. Let me go ahead and put it as 0 there. So we evaluated them both twice. They're exactly the same pieces. Do I have them all in there correctly? I think I had them written down incorrectly. There was a plus here. That's what happens when you're not looking at the sheet that has all the antiderivatives on it. Lots of pluses. How about we just change them all to pluses where they should have been? Better. Okay, it's all good, right? Plus. Okay. So the first piece is -2, and the absolute value of -2 is 2. Minus, so what I have -2 times 1/2 would be positive, or it would be -1. Is the natural log of 1/2, just can you get me a value in terms of, is it bigger or smaller than the 1/2, or than the -1 I already have? It's -0.69. So when I take, so here's what I have right here. Now I've got absolute value of -1, and you said it's -0.69. Okay, so they're both negative, right? So this is going to be an all-out negative number. So what happens when I take the absolute value of negative numbers? I made their signs positive, right? So on this one, because they're both negative inside there and they're combined together, I actually have minus, and then I'm going to take their absolute value. So this is actually going to be the 1 plus the natural log of 1/2. So I'm taking them out of the absolute value, the one that's right here, and they are taking them out and changing their signs because they were negative inside. Plus, the next absolute value is the same thing I just wrote down, but I'm supposed to, again, change their signs, right? So this is supposed to be 1 plus natural log of 1/2. Okay, I've done something. Where's my piece that I did wrong? Oh, I know what's wrong. My absolute values are in different places on my my screen on here than they are in my notes. Let me see if I can figure out why. Oh, because I'm supposed to be taking the absolute value after I evaluate. I'm sorry. Remember I put those absolute value signs in there? The absolute value sign should have gone on the outside of this. Yeah, that's what's wrong. I got my absolute value in the wrong spot. Okay, the same thing's true over here on the right. Absolute value, so we would have done pi over 3 and 0, and then absolute value on the outside of that. I think I've got too many lines there. There we go. I think that's still too many lines. Not enough lines now, but all right, so here I would have had this. Here's my minus. And then over here, here's the minus. Okay, let's try this again down here at the bottom. Okay. On the first part, I have -2, and then I have minus a -2 times 1/2, so this is plus a 1. Did I get that right? And then I have minus the natural log of the 1/2. So -2 plus 1 minus natural log 1/2. Then I have plus, on the second piece, I have -1 plus the natural log of 1/2, and then plus a 2. Yes, they should be the same thing. Are they? Okay, that's good. They should be the same thing because we talked about the graph, the fact that this graph is symmetric. So this is actually going to be -1 minus the natural log of 1/2 plus 1 plus the natural log of 1/2. And they're the same thing because it's absolute values, right? So these two are actually equal to each other. So I have basically 2 times 1 plus the natural log of 1/2. So this is 2 plus 2 natural log of 1/2. Promise they're not all so funny with all the absolute value signs. I just put my one in the wrong spot because I was working too fast. Okay. Okay, so there's really not a lot of difference in this section between what you did before with your integration. The differences come where you have to decide where graphs intersect. That's an algebra question, right? Set them equal to 0, or not equal to 0, but equal to each other, and then often set them equal to 0 to solve, like we did on the second problem, which was our first actual example right here that we worked through, that one. And sometimes they do give you the limits of integration that you need, like on this one where they actually told you you're going from negative pi thirds to pi thirds. And sometimes they do overlap, so you really need to graph them in order to know what you're working with. If we had done this particular equation and we had not separated them at 0, our answer at the end of this problem would have been 0. Why? Because they were the same value, right? The picture here is the same. We talked about how it was symmetric, but the graph that's on top switches. So do you remember how when you did that very first in Calc 2 or Calc 1, when you were very first learning integration, is that if there was this sort of a balanced amount below the curve and a balanced amount above the curve, it sort of zeroed itself out. That's what would have happened on this problem. We would have gotten an answer of 0. So you have to take a look at the graph and see, does it cross each other? And either use the absolute values or decide which graph is on top if you don't want to deal with the absolute values, which ended up kind of making a mess in this particular problem. And so you have to take a look at the graph to make those determinations. Does that make sense? All right.